time we started chapter 3. So we talked a little bit about the supports. So we have spring or a simple support. We can use a rope to hang something, or we can, for example, use a spring to hold it in place, and or you can just put it on some smooth surface to hold it in place.
Yeah.
These are the very basics in terms of support. Later on, we'll get to more proper support, but for now, we're going to stick to that. Today, I'm going to start talking about the free body diagram. First, so, okay. The free body diagram, you probably had it from the physics, you work on that, but the entire thing is that this is how we are going to do the free body diagram. So assume I have a chair sitting on the surface on the ground, on the floor. I want to draw a free body diagram of that. So these are the steps that we are going to do. The very first step is that disconnect that object that you want to draw its free body diagram from anything. So assume it is like suspended in the air somehow. It's not connected to anything, it's not sitting, nothing attached to that. Just the object itself suspended in the air like that. So disconnect the object from all the supports. That's the first step. Object from all supports. So now I have an object, as you know, suspended in the air. Nothing is connected to that. The next step that I want to do is that I want to put all the forces that wants to move that object or make that object moves. They are what they call it the active forces. The active forces are the forces that wants to make the object move from its position to another position, wants it to move. So, yes.
Isn't it also things that want to stop it from moving, like friction?
No, right now we're just looking for all the forces that wants to move. So in the second part, we'll put all the active forces on that. So all active forces on object. The other word, put all forces that want to move the object. In the third steps is what you said. Now you are going to put all the forces that wants to prevent the object to move. Or in other words, all the forces that wants to hold it in its place. It's called the reactive or the support forces. So in the third step, we will put all the reactive forces on the object. In other words, all forces that want the whole object in its place. Which again is going to be the support forces. So here, if I go ahead and say, okay, I have that chair, it's a simple example. So for that chair, the first step is that I will suspend that chair in the air. So no floor, no ground, no nothing. So there's only a chair. It's like suspended in the ground, nothing connected to that. The next step is that I want to put all the forces that wants to move that chair. What forces wants to move that chair?
Gravity.
The gravity or the weight. So the only forces that wants to move it is the gravity, as soon as applied there. So the gravity wants actually to move it. And the forces that wants to hold it in place,
The ground.
the reaction from the ground. The reaction from the floor is the one that wants to hold it in place. So I will go ahead and put them here. So this is okay, you're gonna have the N here. And have the N here. So there it's my free body diagram. Question?
Do we need to worry about friction or anything?
Later in one chapter we touch the friction,
Okay.
but usually you have the friction when the object is about to move or move.
Okay.
So for the statics, we don't care what, nothing is moving.
Yeah. Static.
Yeah, but we will look at the point that the object wants to start to move.
Okay.
But that's the only place we're gonna look at for now. So let's look at this example we have. Swing. We have ball. We have like that. And there's a wall sitting. And this go off on there. There's a spring. Top there is fully console connected to the other. Assume I have this object sitting like that, and it's all the A, B, C, A, B, C, D, constant of K, and E. So it wants us to draw the free body diagram for that. So in that case, if you want to look at it, you're going to draw the free body diagram for three parts of that: for the weight or the ball itself, for the CE, and for the points. So remember, you're going to draw that for that. Depend on which part of that problem you want to work it, you're going to draw the free body diagram for that one. But for example, here for that sphere or ball that I have here, if I draw that, so free body diagram first, disconnect it from anything connected to that. So I'm going to have it only the ball itself. So now next, the driving force, what wants to move it? So it's gonna be the weight. So the only thing that here wants to move is gonna be weight, and it's gonna be downward. Next, all the forces that wants to hold it in place. So the forces that wants to hold it in place is the reaction from this slope, reaction from this slope, and that rope. So we're gonna have three of them. So I have the tension in the rope, I have reaction here, I have reaction here. That wants to hold it in place. Now if I want to draw the free body diagram for the CE,
Letter C, you said.
just the CE, the CE part,
Okay.
the rope CE. So if I want to draw the free body diagram for CE, the same thing, just grab off the CE, like nothing's connected to that. So it's gonna be CE there, like nothing connected to that. And if you look at it, that's it, that's a rope. The rope only have tensions. Rope cannot have any other forces. The force cannot be, remember it says, if you have a rope, the force in the rope will be always tension and always along the rope. So you are gonna have the tension here and the tension here. You can assume one of them wants to move it, the other one wants to hold it in place.
Wouldn't they both want to move it, and then since they both want to do that, it causes it to stay in place?
If both of them, yeah, you can say that, but in reality it's like that. The tension here wants to bring the rope down.
Yeah.
The tension here wants to hold it in place. The one that's connected to the ball wants to bring it down. The ones that's connected to that joint want to hold it
Yeah.
there. Now, what if I want to know the free body diagram for the C, for the joint C? So let's say okay, it's a joint C. What's the free body diagram for that? So if it's a joint C, so first of all I just draw the joint, nothing connected to that. The second, what wants to move it?
So, just to be clear, is C connected to a wall? Like, is it, or is it just hanging there?
No, C is, it's in equilibrium, so nothing move.
Yeah, but like,
But here is connected through the spring to the wall,
okay.
and here connected to the wall through just the rope.
But there's no wall in the background. Alright. So, what forces want to move the object?
The point C. Definitely the tension in the rope wants to bring it down.
Yeah.
So,
Would its mass also want to bring it down? Like its weight?
assume it's massless. Remember when we talked about the rope and things, you said okay,
Yeah.
no mass for the rope for now. So the tension wants to bring it down. Look at here, the CD part. Assuming that it's stretched,
Okay. Well then yeah, K would also want to
then also it wants to
move that way.
move
the
it that way.
The spring force.
The spring force wants to actually move it toward. Is the spring supposed to be a support, but in this case, it kind of wants to bring it the other way. Eventually, play as a support, but then we have the force here in CD, in direction of the CD. And then you have the tension in the CV, which for sure wants to hold it in place. This one's the tension in the CV. I have a specific name for that, I can't remember what it is. So after that we can draw this system of forces for any object that we are given, so we can draw all the forces. The next thing that we want to look into is the equilibrium of the object. So it's going to be 2D equilibrium. So for the 2D equilibrium, basically was that if something wants to be equilibrium, it means that if we add all the forces together, it should become zero. So if I go ahead and say all the forces that applied on any object, so let's move. For this case, you're looking at the particle. That's going to have a particle, and different forces applied on them. So it's in equilibrium only if I can write that equation. I can rewrite that equation because it's a vector, so I can say that, okay, you know what, I'm going to write it in the Cartesian form. So I'm going to write it as sigma f xi plus sigma f yj should be 0. So it's in equilibrium only if that happens. And when this will be 0? There's only one condition that can be 0.
No other components have to 0. Or
The
cancel each other out.
The only way that it can happen is that both sigma fx and sigma fy become 0. Because I and j is not 0, so the only way that it can be 0 is that sigma fx should be 0 and sigma fy should be 0 at the same time. Both of them at the same time should be 0, otherwise it cannot be 0. So that's the, let's say, okay, now that I know that, forget about the scalar format, the Cartesian format, the vector format, we just write it like that. Sigma fx should be 0, sigma fy should be 0. So that's the condition for an object to be in equilibrium in 2D. So to solve it, to solve the 2D problem, the steps that we are going to take is going to be like that. So the procedure solve the 2D equilibrium problem. So the first step is that is draw the free body diagram. And the step 2 is part of the first step. I was going to just put it there in, um, just make sure that you remember that apply all active and reactive, or in other words, supports, forces on object. The third step after you do that is just you'll go ahead and you will find a component or find the x or y component for all the forces. Find x and y component for all forces, and step 4, the last step, just write the equilibrium equation. And solve. So you're gonna write there. Sigma fx 0 and sigma fy 0. And you will solve. Sometimes you can solve them one by one, sometimes you have to solve them simultaneously together. So, one point, when you're drawing this free body diagram, sometimes it's like that you can guess the direction of the forces or the reaction. What if you cannot figure out the direction of the force or the reaction? The drawings will say, okay, apply all the active and reactive forces, and when you want to put it there, you have to know the direction. By the direction, I mean, you know the direction, but you may not know the sense. You don't know, for example, this going up or going down. For example, here for the spring, we assume it is a stretch, but we might not know it's a stretch or not. If we don't know if it's a stretch or not, it might be compressed. So if we don't know the direction, we don't know if the spring force is this direction or the other direction. What will we do? As I said, sometimes we're clear the direction, but sometimes not. Any suggestion? If force is unknown, and you could not find or guess the direction or the sense of the force, so if you cannot find if you don't know the sense of this, if you do not know the direction, and by direction I mean the sense, not because usually you know the line of action, the direction of the force. find out the direction of the force, then assume a direction for the force if assume direction if magnitude of the force calculated to be negative, the direction it chose or the force is in opposite direction. Force is in opposite direction. So let's simple form. Just assume a direction. Assume a direction. Do all your calculation. If the magnitude is positive, means the direction you assume was correct. If the magnitude becomes negative, means that you choose the wrong direction, it's going to be the other. Okay? So, if you get to the point that, for example, here for the CD, you couldn't figure out it's going to the left or it's going to the right, just assume it. If the magnitude was positive at the end of the calculation, means that the direction you chose was correct. If it was negative, it means that it's going the opposite. So never try to, if you figure out just by looking at it, that's what it is. If you couldn't, don't spend time on figuring out the direction. Just choose one. Usually, for example, if it's along the axis, it might be easier just choosing along the axis. You think the positive direction. So any question up to here? So, example. Let's look at an example. So assume there's a weight hanging hanging like this, it's going off, and there's a point going here, and then goes up there, one road, and then there's another road. So it's hanging like that. So this is 60 kilogram. So, says that if you have that, what's the tension in the BA and BC? So we want to know how much tension we have in the BA and BC. Okay. So if I want to find the tension in BA and BC, what do you draw for the free body diagram?
Draw free body diagram for A, B, and C, or just B.
Agree, disagree?
I think if you want all of those things, that you need all of them. Yeah.
So I want to find the tension in these two rows, but I know that I cannot find the tension in these two rows without knowing the tension in this one. So the first thing I'm gonna do is that I'm gonna say, okay, I want to find the tension in this one. So to find the tension in the BD, I'm gonna draw the free body diagram for that weight that I have. So if I draw the free body diagram for that, is the weight, and this is the 60 kilogram. So driving force for that weight is actually the weight. So it's gonna be weight, which is gonna be 60 times 9.81. The one that wants to hold it in place is the tension in BD. So first step, draw body diagram, put all the active and reactive forces on that. Find X and Y component. So look at it. All the forces are already in the X and Y direction. So I don't need to find any X and Y component because all of them are in the Y direction. And then I want to write the equilibrium equation. So if I want to write the equilibrium equation for this one, the sigma fx is 0. That is going to give me anything? The sigma fx is 0. It's not going to give me anything, but there's no forces in the x direction. Then I'm going to write the sigma fy 0. So if I write the sigma fy 0, remember when you're writing it, make sure that you get the positive in the positive. So TBD is going up, so it's going to be positive. Weight going down, so it's going to be negative. So it's going to be, right here, TBD minus W is 0. So TBD is W, which is 60 times 9.8. So any question up here? Now that I have the tension in BD, I can go ahead and try to find out the tension in the other two. So, if I want to find the tension in the other two, the point that gives me the best chance to calculate it is the joint B. So I will go ahead and draw out the joint B. Okay? So if I draw the joint B out, so what are the active forces on that? What wants to move it?
Tension of
So,
BD.
the tension of BD actually wants to move. So I have the tension of BD going down. Let's see. I'll draw the X and Y axis. X. Y. E. X. Y. E. So the first one that wants to move it is the tension of B. So going down. That's going to be T, B, D. The wants to hold it in place is the tension in the BC and tension in the BA. You agree? So tension in the BC and BA wants to hold it in place. So I'm going to have the tension in the BC and the tension in the BA. So I draw the object, I apply all the active and reactive forces. Now I want to find the X and Y components. Okay, so I want to find the X and Y component for each of them. So the TBD is already in the Y direction, so I don't need to be worried about it. What about the TBC? So I know this angle is 45. So this is going to be TBC cosine or sine.
Cosine.
That's going to be cosine 45. Because it's next to the angle. And this one's going to be TBC sine 45. That's away from the angle. Now here, for the TBA, look at here. If this is alpha, look at here. If this is alpha, this angle in that triangle would be alpha too, right? So what would be cosine alpha? Here in that triangle, cosine alpha.
Cosine alpha equals 4 over 5.
Cosine alpha is 4 over 5. The one next to the angle, and the sine alpha would be 3 over 5. So now I can come here and say, hey, this one is going to be TBA cosine alpha, and if this is alpha, and this one is going to be TBA sine alpha. Is it right? So now I will go next step. I have all of them now in the X and Y direction. Now that I have all of them in the X and Y direction, I will write these two equations. I will write sigma of x0 and sigma of y0. So if I go ahead and write the sigma of x0, sigma of x0. What forces do I have in the x direction? I have TBC in the positive, so it's going to be TBC cosine 45. And then I have TBA in the negative. cosine alpha. Any other forces in the x direction? So that's only these two. So it's gonna be 0. Now, if I write the sigma Fy is 0, in the y direction, I have TBC sine 45 plus TBA sine alpha minus TBD is 0. And I have these two. So now I go ahead and write it in here. So I can write it TBC cosine 45 or sine 45 minus TBA sine alpha, which is what the 2 phi, 0. And then I have TBC sine 45 plus TBA sine alpha cosine that's 4 sine alpha, which is going to be 3 phi, is equal to 60 times 9.1. Remember that this was 4 over 5, this was 3 over 5, and this was 60 times 9.81. Any question? So plug that in your calculator and see to get the TBC and TBA. TBC. Get your calculator.
I figured if you say it out loud.
No, that one will work. I will make sure that you know how to do it. So make sure that you know how to do the simultaneous equation solver, how to use the simultaneous equation solver in your calculator. I'm gonna just give you, look at here, if I have a system of equations like this, as a1x plus b1y is c1, and a2x plus b2y is c2. If I want to write it in the matrix format, you might have it in some of your, did you have the engineering calculation course or something like that, that teach you the numerical method?
Engineering.
numerical method for anything.
I don't recognize the name.
So it is that if you have something like that, I want to give it to the computer or to the calculator, I have to write it in form that the computer can understand. For that, I have to put it in format of matrix. So if I want to write that matrix, it's gonna be like that. These sets of equations. The first matrix is gonna be my coefficients. It's gonna be A1, B1, A2, B2. The coefficient. The second matrix is going to be my unknown. And the third matrix is going to be my constant. In calculator or in computer, when you want to enter it, usually they say, okay, what are the coefficients, what are the constants? Some of them might be more friendly and just write it like that. But if it gets to 4 equation, 4 unknown, 5 equation, 5 unknown, usually they want you to enter it like this. So let's do it for 3 equation, 3 unknowns. If I go ahead and assume I have 3 equations, 3 unknowns. So a1x plus g1y. And just to make sure you guys are not going to get confused, write them b1 and b2. Plus c1z is assumed d1 a2x plus b2y plus c2z is d2 a3x plus b3y plus c3z is d3. Now if I want to write them as a matrix, the constant is going to be a1, b1, c1, a2, b2, c2, a3, b3, c3. Then x, y, z. And then you have the constant b1, b2, b3. Here, this equation I have. If I want to write this equation in this form, so I'm going to go ahead and write that equation. So it's going to be cosine 45 TBC minus 45 TBA is 0, and then I would have sine sine 45 TBC plus 3/4 of TBA is 60 times 9.8. Now if I want to write it that way, it's going to be cosine 45 minus 4/5 sine 45 3/5. The unknown is TBC, TBA. The constant is going to be 0 and 60 times 9.81. So plug it in your calculator.
475.66.
So for which one for BC?
For TBC, yeah.
So TBC is
475.66. 475.66.
And for TBA,
2,943 over 7.
2,940.
3, and then divided by 7.
Divided by 7.
Yeah.
Yeah.
That's what it told me. Or 420.43.
Say that again.
420.43.
424.
420.3.
0.43.
0.43. So just 20.43. Yeah.
With the 0.
420.
There we
There we
go.
go. Wait, how did you just typed in the
We
equation?
just type in, so it's cosine 45 x.
Then enter.
Yeah.
And then, oh, negative 4.
So in that format that I write it up there, it's going to be A1, it's going to be B1, it's going to be A2, it's going to be B2, it's going to be D1, it's going to be D2, and it's going to be X, X, Y.
That's 60 times 9.81. What is it? Okay.
That's the way